Hey everyone, welcome back to Calculus 2. This will be the 30th lecture of the course, and actually the final lecture of the course. And in this section we're going to discuss, kind of introduce the idea of Taylor and MacLaurin series. Okay, so let's hop into it. Okay, so we'll call this section 4.8. This is, I'm just going to write Taylor series, but we mean Taylor and MacLaurin series, and MacLaurin series being the special case of a Taylor series centered at c equals 0. Okay, so kind of the way to start this would be to say, well, previously we derived power series for several different functions, using geometric series in the main with term-by-term differentiation and integration. Okay, so that's kind of how we've done it in the past up to this point, right? And so in this section we're going to study a general procedure for deriving power series for a function that will have derivatives of all orders. Okay, and that's going to be the Taylor series. Okay, so let's talk about, let's just jump right into the theorem here. So if f is represented by a power series, okay, so by a power series, and we'll say that power series is f of x equals the sum from the a of n times x minus c to the n. Okay, so if it's represented by a power series like this, and then we'll say for all x in some open interval containing c. Okay, then a sub n is equal to the nth derivative of f evaluated at c divided by n factorial. Okay, all right, so this we've seen, and f of x is equal to f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus plus the nth derivative of f evaluated at c over n factorial times x minus c to the nth power, and so on. Right, so that would be the series, right? Okay, so we've kind of talked about this already, but this is kind of the basis for what we're going to build the Taylor series on. Basically, this is the Taylor series, and we'll see that in a second. But what we want to do first is we want to make sure that we buy this. Okay, so if f is represented by a power series f of x that has a form like this, right, where you've got the sum, and then you've got some an piece for each term, some an factor, and then x minus c quantity raised to the nth power, and this is the form, and f is represented by this and equal to this for all x in some open interval containing c, right, c being the center. Then the coefficients are, f, nth degree of f, nth derivative of f evaluated at c over n factorial, and the function looks like this. Okay. All right, so let's prove this. So for this one, we'll start. We'll assume is kind of the statement here. So suppose that the sum a of n x minus c to the n, right, has a radius of convergence r. Okay. Then we know that the nth derivative of f exists, and for So we know that the nth derivative of f exists for all x where we're inside of the interval defined by c minus r, c plus r. Another way to write that would be all x such that the absolute value of x minus c is less than r. Okay, and by successive, and we could differentiate such a series, right? So by successive differentiation, what do we get? Well, we can just go through it, right? So the f of 0 of x is equal to the function itself, a0 plus a1 x minus c plus a2 x minus c squared plus a3 x minus c cubed, and I'll go out to the fourth term. All right, and so on. Okay, then what's the first derivative? Well, we've seen this before. A1 plus 2a2 times x minus c plus 3a3 times x minus c squared plus 4, right? 4a4 x minus c to the third power plus, and so on, right? So basically this is kind of doing one of these, right? Because as we differentiate successively, that constant on the front is going to drop out. What about the second derivative? Let's just build up the pattern. Second derivative will be 2 times a2 plus, and here's where we can start to see the factorials. It would be 3 times 2, so 3 factorial, a3 x minus c plus 4 times 3a4 times x minus c squared plus dot dot dot. And if we do maybe the third derivative, that's where we'll see 3 factorial a3 plus, hold on 1 second, plus 4 factorial, right here the 2 will come down and you'll get 4 factorial a4 times x minus c plus dot dot dot, right, and so on. And if we keep going, right, the point is just see where this, to make sure we see the pattern in the constants. The nth derivative is going to be n factorial times a of n plus n plus 1 factorial times a of n plus 1 plus dot dot dot, right? Okay. All right. And so this is kind of the pattern, right? This is the pattern that we see here, right? The way the differentiation will, well, no, that one doesn't really work, but the way the differentiation will successively bring the powers down front, and you get this factorial form. Now, what happens when we evaluate each of these derivatives at x equals c? Right, what happens? Well, the function itself evaluated at c gets us 0 factorial, right? Now, times a0, sorry. All right, so hopefully we can see that, right? All of these terms would be 0, right? You get a 0 here, you get a 0 here, and what you're left with is that. So the first derivative evaluated at c gets us what we could write as 1 factorial times a1. f2, second derivative, evaluated at c leads us to 2 factorial times a2, and so on, so that the nth derivative evaluated at c will be n factorial times a of n. Okay. And so this pattern should be clear. Let's just make sure that we see all that, right? If I look at this guy here, differentiate or evaluate at c, then again all these terms will zero out. I'm left with this, which is just going to be the 1 factorial times a1. If I evaluate the second derivative at c, these all zero out, and I'm left with this one, which is 2 times, you can think of this as 2 times 1, right? And then the next one would be 3 factorial, and then finally 4 factorial, 5 factorial, so all the way down to n factorial. Okay, so that's just what happens when we evaluate the derivatives at c. We get this pattern, and of course we can see that this implies that a0 is f of 0 evaluated at c over 0 factorial. A1 is f of 1 evaluated at c divided by 1 factorial, and so on, right? And really the one that we care about is what happens with the nth coefficient, so a of a sub n, that is the nth derivative evaluated at c divided by n factorial. Okay, which is the result. That's what we were after. We just want to make sure that we can see exactly where these coefficients are derived from, and they're coming off of the power series. Okay, all right, so then let's, so important, right? This is important. Notice, right? Notice that these coefficients of the power series are exactly the coefficients of the Taylor polynomials for f, with centered at c, right? And we defined this previously. So these coefficients are exactly the coefficients of the Taylor polynomials we saw previously. Okay, so it's exactly what we saw previously with the Taylor polynomials, and that leads us to the definition of the Taylor series. Okay, so the definition of the Taylor series. So, and this is the Taylor series. So if a function f, if a function f has derivatives of all orders at x equals c, then the series, so here it is, n equals 0 to infinity of f, nth derivative of f evaluated at c over n factorial times x minus c to the nth power, right? So this is your coefficient, this is the x piece of it. So this is equal to f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus so on. Okay, so this is called the Taylor series. The Taylor series, and I guess we would say it's the Taylor series for f at c. Okay, and so if c equals 0, it is the MacLaurin series. Okay, so that's the definition. So what does this tell us? Well, it tells us that if you know the pattern for the coefficients of the Taylor polynomials for a function, you can extend the pattern easily, to form the Taylor series for the function. Okay, so if you know the pattern for the Taylor polynomials, you know the pattern. You can easily extend that pattern to form the Taylor series. Okay, so let's tie those two ideas together here with an example. Let's tie those two together. So we saw previously that here's a Taylor polynomial, a 4th degree Taylor polynomial. So we saw that p sub 4 of x, where it was equal to x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 to the 3rd power minus 1/4 x minus 1 to the 4th power. We saw this polynomial here was the 4th degree polynomial for the function f of x equals the natural log of x, okay, centered at 1. Okay, then the Taylor series that we can base on this is we can base Taylor series on this is going to be, let's write it out, x minus 1 minus a half x minus 1 squared plus a third x minus 1 to the 3rd power plus dot 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 plus, now there's this alternating piece in it, so there's the -1, and it looks like it should be an n plus 1 on that over n, and then it's just x minus 1 to the n. Okay, and so we could write this, and this would be a series, so I'd continue on, but we could write this as the sum from n equals 1 to infinity of -1 to the n plus 1 over n, right? That captures all the coefficients, you can see that clearly, and then x minus 1 to the nth power. Okay, so that would be the Taylor series based on this polynomial. Okay. All right. Excellent. Excellent. Let's take a look at another example here. So here what we're going to do is we're going to use the function f of x equals sine of x to form the MacLaurin series and that'll be this guy here, n equals 0 to infinity of f of 0, that's the nth derivative, divided by n factorial times x to the n. Okay, so we need to know the pattern of the coefficients. Okay, and the pattern is going to come off of the function f, here, sine of x. Okay, so let's figure out what that looks like. So f of x equals sine of x, f prime of x equals cosine of x, f double prime of x equals negative sine x, f triple prime of x equals negative cosine of x, right? And then the pattern will just repeat itself. We'll hop back to sine x. So you can see that we're going to hop right back up here. And so f of 0, that's sine of 0, which is 0. F prime of 0 is cosine of 0, which is 1. Okay. Then f double prime of 0 is negative sine of 0, which is again another 0. And the third derivative, f triple prime of 0 is equal to negative cos 0, which is -1. Okay. So the pattern of the series, the coefficients appear to be 0, 1, 0, -1, 0, 1, 0, -1, right? So that's that's going to be the pattern going as the derivatives increase. That's the piece we need. And so then the power series, flip the page here. Then the power series is, so it's sum n equals 0 up to infinity of f, nth derivative of f evaluated at 0 in this case over n factorial times x to the n. Remember, this is the MacLaurin series, so it's centered at 0. And we can write that out. It's going to be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus the third derivative evaluated at 0, 3 factorial times x cubed plus, and so on. And so a couple of things to notice here is that, this is going to be 0, because that coefficient will be 0. This is also going to be 0. The fourth degree term will also be 0. Okay, and so what we're really left with here is f prime of 0 plus f triple prime of 0 over 3 factorial x cubed plus, now we know that the fifth degree term will be up in here as well. Or sorry, not the fifth derivative. Right, and so on, and you'll have like the seventh as well. And so on, right? So it'll look like this. And we also know that there's going to be some flipping of the terms, right? So this one will be positive, this one will be negative, this one will be positive, this one will be negative, right? So remember, that's just these two, right? You're going from 1 to -1. So we've taken the 0 terms out, and so it's going to oscillate back and forth between 1 and -1, right? So 1, -1, 1, -1. Okay, and so when we kind of consolidate all of this down into a really concise expression, we would say n equals 0 to infinity, that sum, and then you're going to have the oscillation handled by this -1 to the nth power, and then you'll have x, and it'll be 2n plus 1, right? So that would be like 2 times 0 plus 1 gives you the first term, 2 times 1 plus 1 gives you the second term, which is the third derivative in 3 factorial. Okay, and then over 2n plus 1 factorial. Okay, so this would be this would be the power series. Sorry, the MacLaurin series, I guess, that's formed using the Taylor coefficients for the function f of x equals sine of x. Okay, now, question, does this series converge? Well, it does certainly at 0, but where else does it converge? Can we quickly see that? It's the same tools will be applied here. So we can look at the limit as n goes to infinity of the n plus 1 term over the nth term. We can use the ratio test. All right, so we can test this quickly, and we'll see that yeah, indeed it does. So like plugging in the n plus 1 term to start with. So this would be n plus 1, and then x of 2n plus 3 over 2n plus 3 factorial, and then all of that would be divided by the nth term here. So I'm going to invert and multiply. So this would be 2n plus 1 factorial over -1 to the n, and x to the 2n plus 1. All right, and a lot of stuff will cancel here. Right, so basically up top we're left with just a -1 and x squared. And then down below, you're going to have, these two will cancel somewhat, but you're left with two factors here. So 2n plus 2 and 2n plus 3. All right, so that's what it looks like. And we know that this is going to be 0, isn't it? It doesn't matter what x is. It doesn't matter what x is. As n gets large, it's going to overtake whatever x is, and this ratio will be 0. Okay, so that, what does that imply, right? This implies that the interval of convergence is all real numbers, right? Basically, the radius of convergence is infinite, and the the series converges for every real number. Okay, so this is great, right? This gives us a really quick way to generate a power series from using the methods that we've had previously explored, of Taylor polynomials, sorry. And we call them Taylor series. Now, an important thing to note here is to, notice, right, from this example that, we cannot conclude, right? We can't conclude that the power series converges to sine of x for all x, right? That's important. what we say is that it converges to some function, but we're not sure which function it is, right? So in order to say that a series that's derived from Taylor polynomials built around the signed function, we have to prove something additional, right? We have to prove something about the remainder of the Taylor polynomials, right? And so in order to do that, well, let me just recap that. So we built this series using f of x equals sine of x. But we cannot say that the series converges to sine of x for all x and r. For all x, real number valued x. What we can say is that it definitely converges to sine of x at its center, right? That's what it's built on. Now, whether it converges everywhere, it requires a little more work, okay? To show that it converges everywhere, we need to prove something about the remainders, right? So when we have a Taylor polynomial, you may recall that it's an approximation, right? And as we move off of the center, the approximation becomes less and less precise, right? It becomes more and more of an approximation, right? So less accurate. And so what we need is we need to discuss quickly what we mean by the remainder of a Taylor polynomial. Okay, what is the remainder of a Taylor polynomial? So if we approximate f of x with, some nth degree polynomial, we'll call it p sub n x, okay? We should expect some remainder. Right, and what we would say is that f of x is equal to the approximation plus the remainder. And we'll denote the remainder by r sub n of x. Right, so f of x is going to be roughly equal to p of x plus some remainder. Okay, well, precisely, this would be precise, but p is just an approximation, so there's always going to be this error term. Okay, and so to be a little more precise, we say that r of n, the absolute value of the r function, is equal to the absolute value of f minus p sub n. And we call this the error. Okay, and this is the error associated with the approximation. All right. Okay, and so let's talk about what is this remainder term, this error term. Okay, so theorem. Okay, if a function f is differentiable through order n plus 1 in an interval I, so on an interval I containing C, then for each x in I, there exists there's going to exist some number z between x and c, okay, such that what? Such that f of x is equal to f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared plus dot 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 plus the remainder at x. Okay. Now, what is this remainder? Where r sub n of x is equal to, okay, it's equal to f of n plus 1. So this is the n plus 1 derivative evaluated at some value z, which is between x and c, divided by n plus 1 factorial times x minus c to the n plus 1. Okay, so this is the form of the remainder. Okay, for some z. The z is not known. The z can be found, but for some z between whatever your value of x is and the center of the Taylor polynomial, the remainder is going to be this given by this statement. Okay. Okay. Let's see an example. Maybe an example will help clear any confusion, I think. So example. Let's take f of x equals sine x. Then we know that p3 of x, we can calculate, we think we've calculated before, I think we just calculated actually. X is going to be x minus x cubed over 3 factorial. Okay, so this is the third degree Taylor polynomial for sine of x. So what we want to do is let's approximate, let's use p3 to approximate the sine of 0.1. Okay, and when we say approximate, we mean determine the accuracy of the approximation as well. So pull and figure out what that remaining piece is. Right, so we've got a function sine of x, we've got a corresponding third degree Taylor polynomial, and we want to use the Taylor polynomial to approximate sine of x when x is 0.1. Okay, all right. So let's check this out. Let's run through this. So basically, we're just going to use the previous theorem to approximate this. So we'll use the previous theorem. Okay, and so what we can say is that sine of x is equal to x minus x cubed over 3 factorial plus a remainder. Right, R3 of x in particular. All right, so it's equal to x minus x cubed over 3 factorial, and then plus, what's the remainder? The remainder going to be? It's going to be the fourth derivative, evaluated at some z divided by 4 factorial times x to the fourth. Okay, so this is the remainder here. Okay, and now note, z is in the interval 0 to 0.1. So it's going to be somewhere in there. Right? Okay, you can just pick. Okay. All right. Okay, so then, we can look this up. We can see the sine of 0.1 is approximately 0.1 minus 0.1 cubed over 3 factorial, right? So just plugging in the expression, or the value, and we get, this is 0.1 minus, now I've done this calculation ahead of time, and it's 0.000167, right, which is approximately 0.099833, right, so right about there. Okay, and so that's just the approximation from the Taylor polynomial side. So we haven't got the remainder yet, but let's look at the remainder now, because the fourth derivative of f evaluated at c is going to be sine of z. Now we saw this earlier, right? You would have to figure out what that fourth derivative was normally, but we kind of had it. We've seen this one before. We know that it kind of flips back to the original function at the with the fourth derivative. So because of this, it follows that the error, right, so the error R3 0.1 can be bounded. Can be bounded by, right, so first of all, on the low end, 0 is less than R3 of 0.1, right, so we know the error is positive, okay, and we know that the error is equal to sine of z over 4 factorial times 0.1 to the fourth. Okay, we know that that's less than 0.0001, okay, over 4 factorial, right, which is, this here is approximately 0.000004, okay. So basically what we're able to say here is that the remainder here is somewhere between, it's greater than 0, but it's less than, strictly less than 0.000004, right? So then all of this would imply, right, this is just the remainder. This is going to imply that, sine of 0.1 is somewhere between 0.099833. Now this was strictly the P4, right? That's what P4 is. We know that that's low, right, because there's a bunch of terms left off, right? And this is we know that sine of 0.1 would be equal to basically 0.099833 plus R of 3, which would be less than the upper bound here, right? So it's less than 0.099833 plus 0.000004. Okay, and so what is this? This is P4 plus, this is P3 plus R3. Right, we know. So it's the third degree Taylor polynomial plus the remainder for the third degree Taylor polynomial. Okay, so all in, what does this tell us when we're approximating sine of 0.1 using this Taylor polynomial? We know that 0.099833 is less than sine of 0.1, which is less than 0.99 there should be a 0 in there. 99837, right? So really great precision even with a third degree polynomial. Okay. All right. So that's a little aside about remainders. Now sometimes you learn about the remainders in the Taylor polynomial section. Sometimes you learn about it when you need it for Taylor series. So we've elected to discuss it during the Taylor series. Okay, and so basically, kind of getting back to the discussion with Taylor series. What we said previously was that we had an example where we derived a Taylor series from a particular function, sine of x, I believe, right? And we said, hey, we can conclude that the power series converges, but not necessarily to the function from whom we got the coefficients for the Taylor polynomials, right? So when can we conclude that it converges to its source function? That's the question. Okay, that's the question. Okay, so theorem. If the limit as n goes to infinity of r sub n is equal to 0, this is the remainder term, for all x in the interval I, then the Taylor series for f converges and equals f of x equals the sum n equals 0 to infinity of the nth derivative of f evaluated at c over n factorial times x minus c to the nth power. Okay, so if the sequence of remainders converges to 0, meaning the remainders get smaller and smaller as you go further and further out into the series, then basically that tells you that the Taylor series converges. Okay, converges to f. Okay, let's prove this. Okay, we can prove this pretty easily, actually. So for a Taylor series, the nth partial sums coincide with the nth Taylor polynomials. Okay, that's great. That's a big... So basically we can say that S of n x is equal to P of n x. Right? They're the same. The nth Taylor polynomial is the same as the nth partial sum Taylor series. Okay. Now we know, that P sub n of x is equal to whatever the function is minus the remainder. Okay. So it follows pretty quickly that the limit as n goes to infinity of S of n of x is going to be equal to the limit as n goes to infinity of P sub n of x. Okay, and what is that? Well, that's just the limit as n goes to infinity of f of x minus r sub n of x, right? Minus or remainder. So whatever, the p sub n is just the function itself minus the remainder. Okay, all right, that's just algebra up here. Actually, it's not even algebra, it's just given right there. Okay, and so we can break this down a little further. F is not dependent upon n. F is just a function of x. Right, and so this is equal to f of x minus the limit as n goes to infinity of r sub n of x. Right, and when does this equal f of x? This equals f of x when r sub n goes to 0. Right, so if this limit is 0, then the nth partial sums, the sequence of nth partial sums for the Taylor series will converge to the value of f evaluated x. Okay. Very nice, very neat. If you follow the discussion on the remainders, this is really straightforward. The remainder discussion can be a little complex in the weeds, but on the surface, this is a straightforward concept, hopefully, right? It's literally, this hopefully is clear, right? And then if you get that, then this proof is squeaky clean, okay? All right, excellent. So for a Taylor series, we now know that the Taylor series will converge to f if, and only if, really, if the remainders, the sequence of remainders have a limit of 0. Okay. All right. How about a couple of examples, and then we'll call it a day. Okay. So example. Let's pull back up our example with f of x equals sine of x. So consider f of x equals sine of x. Let's, using this same kind of mechanism that we've just been discussing, let's show that its MacLaurin series converges to sine for all x. Okay, right? So we need to show, what are we trying to show here? Well, we're trying to show that sine of x is equal to the sum from n equals 0 to infinity of, now we previously worked this out, -1 to the nth power times x to the 2n plus 1 power over 2n plus 1 factorial. Now this is, again, we've worked this one out, so I'm just kind of jumping in as an example. Right, we're going to take it further. Right, so remember what this looks like. It's x minus x to the third over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus so on, right? It's an infinite series. So what we want to show is that this is true for all x, right? We want to, for all x in R, right? All real numbers, this works. Okay. So what do we do? Where do we start? Well, we can start with the fact, and we start in a number of places, but I think the best place to start is to say that f of x, what's the n plus 1 derivative of f of x? Well, it's going to be equal to plus or minus sine of x or plus or minus cos x. That much we know, there's no question. Okay. And so given that, we know that the absolute value of that nth derivative of x, sorry, I should put a z in here. We're gearing up for a remainder discussion, so let's switch over to z. Actually, I want to use z up here. Well, it doesn't matter. Okay, so the n plus 1 derivative of f evaluated at z, where z is between 0 and c, we know that that's less than or equal to 1. We know it because it's sine or cos x, and those are always, they oscillate between 1 and -1, right? Okay, so nothing really even fancy there. Okay, so we know that this is true for all x in R. Okay, so that means 0 is less than or equal to R of n of x, right, which is equal to, let's write it out here, n plus 1 derivative evaluated at z, again just pulling that remainder out from the previous discussion, divided by n plus 1 factorial times x. This is a MacLaurin series, so it's just x to the n plus 1 power. Okay, and so then obviously that's going to be less than or equal to x to the n plus 1 power over n plus 1 factorial. Okay, so perfect, right? So basically we know that this is just basically -1 or +1, and so it's meaningless inside the absolute value. Okay, so we dump it out. And so now the question is, what happens up here? Because we need to show that the remainder is 0, right, at the limit, right? And so what happens up here? What happens to this as n grows? Well, this is, a little bit of this is slightly hand wavy, but we know that n plus 1 factorial grows much faster than x to the n plus 1 for any x. Right? It doesn't matter what x is, right? Very rapidly, n plus 1 factorial is going to overtake it. So, that being the case, we know then, therefore, that the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial is equal to 0 for any x. Okay, right, so that limit is 0. Right, so then, what happens up here? So then, as n goes to infinity, what can we say? Well, we can say that, you've got 0 less than or equal to your remainder term, which is less than or equal to this, x to the n plus 1 over n plus 1 factorial, and as n goes to infinity, this goes to 0. Okay, so by the squeeze theorem, this is 0, this is 0, this goes to 0, that means this goes to 0. So r sub n goes to 0 as n goes to infinity. Right? And so that being the case, then the MacLaurin series must converge to sine of x. Okay, perfect, exactly as we would want it to be. It's amazing how that can happen. Okay, all right, just one more example, maybe two more examples, and then we'll be done. Okay, so one example would be find the MacLaurin series for f of x equals sine of x squared. Okay, so one thing to notice here is that if you start to differentiate this, it's going to get really messy really quickly, right? So we know that f prime of x is equal to, for example, 2x cos x squared. That one's not too bad. But when I go to the second derivative, now I have to use the product rule here, and I get a big old mess. So this is messy and not workable. It's going to be difficult to spot the pattern, basically. So what we can do is, again, let's pull back up our trusty g of x equals sine of x, which is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus right? So we just saw this. And so can we find the MacLaurin series for this? You betcha. Not a problem, right? All we got to do is consider g of x squared. G of x squared is equal to sine of x squared. And we saw what happens there. Right? Previously we saw what properties of power series, if we exponentiate the argument, it's just like multiplying. Right? So we should get x minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x, this would be x to the 14th over 7 factorial plus right? So that's sine of x squared. Okay. How about another example? One more example. I keep saying one more. I just can't stop. Let's find the MacLaurin series for f of x equals 1 plus x to the k power. So this is like a binomial, right? So f of x is equal to 1 plus x to the k. F prime of x is equal to k times 1 plus x to the k minus 1. F double prime is k times k minus 1 times 1 plus x to the k minus 2, and so on. Right? What's the nth derivative? Well, it's k times k minus 1 times, now what's the last one going to be? Well, we keep dropping these down all the way to n, so what's left would be n plus 1, so k minus n plus 1, and then it'll be 1 plus x to the k minus n, right? So the last term to drop down would be k minus n plus 1, because this is k minus n. Okay, and so what happens when I evaluate all of these at 0? F of 0 is 1. F prime of 0 is k, right? F double prime of 0 is going to be k times k minus 1, and then this is just 1. And f of n of 0, which should be this whole string here, right? So k minus 1, k minus n plus 1. Okay, so we've got that, right? So this is what we need really to form the Taylor series for this guy, right? The MacLaurin series, centered at 0. Okay, and this will produce what does it produce? Well, it gets us 1 plus k times x plus k times k minus 1 x squared over 2 plus, let's just go straight to the, well, we'll do one more, k times k minus 1 times k minus 2 x cubed over 3 factorial plus, and now here's the dot dot dot. I need a little more space here, so dot 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 plus, and then it'll just be k times k minus 1 dot 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 k minus n plus 1 all over n factorial, and then it's just going to be what, x to the n. Right, so this would be the this is like a really general, right? It depends on k, right? But this is going to be your MacLaurin series for 1 plus x to the k. Okay, this is 1 plus x to the k. So let's plug in a real value for k now. Or what about f of x equals 1 plus x to the 1/3, so like the cube root of 1 plus x. Okay, well, it's just going to be this basic pattern. Just toss in 1/3 for k. All right, so it'll be 1 plus x to the 1/3 is going to equal 1 plus x over 3. That's 1/3 times x. And now, you do have to do a little bit of work here for sure. So it'd be 1/3 times 1/3 minus 1 times x squared over 2, and then plus 1/3 times 1/3 minus 1 times 1/3 minus 2 x cubed over 3 factorial, and so on. And so you could work this out to be 1 plus x over 3, and then you would end up with something like, I think this would be negative because that'd be negative 2/3. So it'd be minus 2x squared over 3 squared times 2 factorial, and then this one should be plus. You'd have two minuses there, so it'd be plus. I think you get 2 times 5x cubed over 3 cubed 3 factorial. So you can begin to see the pattern here. Plus dot dot dot, right? You could sort this out. Okay. So, but that would be an example of using kind of this general formula here for a specific k. Okay, all right. So I think we'll probably end it there. And this is actually the last recorded lecture for Calculus 2. So we've done many hours worth of Calculus 2 instruction at this point. So hopefully if you made it this far, hopefully you found the course useful. I would assume so. You would have probably not stuck with it had you not. So congratulations, well done. We will be setting up a Calculus 3 course soon to follow. Probably just keep working. So Calculus 3 is available or coming soon. Okay, and so hopefully we'll see you there. And so until then, everybody take care. Thank you.